Okay, let's get started. Welcome to the week 12 live session. Hope you can hear me clearly and see my screen. If not, leave a message on the chat. So today will be the last live session for this course. So, okay, good to know it's clear. Today will be the last live session in this course, and I think I had a request last week or the week before to include more problems and less of decap. So I've done that for this week. So we have around 15 questions and very little recap. So we'll cover whatever has been asked in the discussion forum and answered. And after this, till the end of the course, the discussion forum will be active even though you won't have live session. So in case you have a doubt about anything, feel free to ask on the discussion forum. Okay, they will still respond to you till the exam, and even if you have some doubts in the exam or the exam answer key, you can use that forum. But live session wise, this will be the last one. And again, as always, I will upload the slides and the recording shortly after the session, and you'll have access to all of that. And if there's any other doubts that you want cleared, you can ask me today. If I'm not able to clear it in today's session, I will try to add a couple of slides into this same week 12 deck before I post it on the link that you will be getting. So feel free to ask questions as always, and we'll solve the questions as usual, and you can post your answers on the chat box. Okay, with that we'll skip all of this, and as usual we'll take a 5-minute break around 8 o'clock. So this week was continuing with efficient neural network training and inference, and we looked further at training, and we moved on from just the forward pass to also the back propagation, looking at how the gradients are calculated, how the partial derivatives, what partial derivatives you need, and further on moving to, so this was all about the workload, right? I was talking about this last week. So you can think of it one part as the workload, and the second part as the optimizations that you can do from a GPU perspective. So we looked at quite a few optimizations that we could do for the GEM, or the matrix multiplication operation. So you'll see a lot of custom hardware, right? Apart from GPUs, there are also a lot of custom hardware designed lately that try to optimize this. And why is this so critical for deep learning workloads? You've already seen, right? In the last class we saw how to convert a convolution operation to a generalized matrix multiplication, to a GEM. And because convolution is the most common layer that's used in CNNs, optimizing GEM means that you also optimize convolution and in general deep learning workloads. So this is done, this is done not only for GPU, not only on the GPU side of things, but also in a lot of custom accelerators that are built for AI, right? And similarly you will see, and again remember one thing from an AI perspective, there are different ways in which you can implement the convolution operation. One is GEM, which you're studying in this course. In other places you might also hear of things like FFT and Vinograd. All of them are valid ways to execute it, and as algorithms they will have different time and space complexities. So you might want to pick a particular implementation on a particular hardware, and that will depend on how fast each of these things are on that hardware. For instance, one type of hardware might be a lot more optimized to the matrix multiplication than say F50, and something else might be vice versa, right? So which implementation you pick for a layer is also a very important part of optimizing deep learning. This is typically done under the hood, right? The user or the developer who writes these models in a deep learning framework is rarely ever exposed to them. It's always done by, say, the deep learning compiler or by CUDA and things like that. And then we looked at a little bit of pruning, a little bit of sparse matrix operations. Again, sparsity is a very highly talked about thing in the field of GPUs. So I think we briefly spoke about flops as a metric of computation, right? So if you go look at current day NVIDIA GPUs, let's say the Ampere architecture, you will also see some GPUs which have computation metrics as sparse tops. So that's sparse and then trillion operations per second or tensor operations per second, right? It's used in both ways. But what that means is, if you have sparsity, the GPU architecture itself is designed in a way to exploit that sparsity. And that's again because in the DNN world, many times matrices are very sparse, right? So if you can find a way to exploit that sparsity and cut down on your execution time, that also brings you performance benefits. And modern day GPUs do this. So what you're learning here is a small overview on what is sparsity and how you can kind of do that. Here we looked at the CSR format and we saw how much lesser storage it takes to save the same matrix, right? And this is used again throughout today's GPUs. So with that, like I said, I don't have any dedicated recap for this week. Wherever needed before the questions, we'll have a quick recap. So we'll just move to the discussion forum questions and walk through them once in case you've not understood some of it. So this was regarding the coarsening optimization we discussed for GEM. So let's read the question since it's quite long. So as per the discussion, A sub global load happens once for given WPT in a tile, but I could not relate this argument if I compare it with the code in lines 9 to 12. Here we are making global loads from A sub and B sub in the for loop up to WPT iterations. So the person is referring to this for loop here, this for loop here. Yeah, that's the A sub and B sub. But the discussion goes here that we will make a single load from A sub and WPT's loads from B sub. In general, okay, so this is the question, right? So the person is asking that we are talking about having a single load from A sub and WPT loads from B sub, but both of them seem to loop up to WPT iterations. So let's see what the answer is. So since this is thread coarsening, we talk about the logic of that first. In general, thread coarsening gives more work to each thread. So again, we spoke about this earlier also, but just for a quick recap in case you were not there then or you don't remember. So what happens is you actually do some memory loads and stores, right? And then you do some compute. Now what happens, let's say I load two things from memory and this takes, let's say this y-axis is time, right? Let's say this takes this much time and I'm only doing this much compute, right? So in a way, this is not very efficient because for this much amount of memory that you bring, you only are able to do this much compute, right? And then again you have to load. So this becomes a memory bound regime. So what you would like to do is for whatever data you're loading, you would like to maximize the compute that you do. This term is also, so just the way we have flops, here I think the memory is kind of measured as how much you load or store, right? Something like that. And there is a term that kind of combines both the compute and memory. It's called arithmetic intensity. So it's kind of the ratio of how much compute you do for every byte that you load from memory, which is very meaningful when we are looking at something like this, right? How much work are you actually doing for what you load? So the logic behind thread coarsening is we are trying to increase the work per thread, right? So what we do here, so now we are summarizing this code that's here. So in line number 6, right, a factor of WPT registers are initialized to 0 for each thread, this one here. After that, during the global memory load, these two, right, 8 to 12, each thread loads WPT values of A and B into shared memory A sub and B sub respectively. That's what you can see happening here. After that, in lines 14 to 16, these two for loops, right, what happens is each thread performs WPT times TS number of accumulation. So TS is the outer loop, WPT is the inner loop. So it's typically the product of these two. But if you notice closely, the inner loop over WPT does not require a new value from A sub each time. So it's actually calling A sub k comma rho. So the k is the index from the outer loop, but notice that W is never used. Whereas if you see B, W and k are used, which means that it keeps loading a new value each time, right? So therefore, accesses that A sub does are reduced by a factor of WPT because it does not have this index from the inner loop used, right? This is a simple way that you can understand this. Just pay attention to line 16. See what are those indices actually being accessed. Then I think it's clear. So you might be confused when you see these two loops. You might say both A and B are actually within this, so maybe it's a product of these two for both. How are you saying A is doing lesser accesses? It's because this actually does not vary. The row index that K uses does not vary. It's not using W unlike B. So I hope that is clear. Okay, again you can pause me anywhere, ask questions if something is not clear, and at the end of the session today again I'll ask once maybe at the 8 o'clock mark and once towards the end to see if you have any specific questions that needs clarification. For now we'll move on. Okay, so the next thing is about the error term and loss function. So these are kind of ML terminology questions, right? Again, ML terminology has seen a lot of change, right? Every now and then people come up with a new word. So it's important to understand what these exactly mean. So the question says, are the error term and loss function that you refer to the same? For example, when we estimate a linear regression model, the error term there is y equal to a plus bx plus e, where a is the intercept, b is the slope, and e is the sum of the deviations of the actual values from the estimated regression line. I'm a little bit confused when you say y equal to f of x comma phi, where phi or theta, whatever according to the notation, is a loss function in lecture 54. Please explain. So this is basically asking about the difference between error and the loss. So the answer says they are different concepts in the context of machine learning and statistical modeling. The error refers to the residual or the discrepancy between the observed data and the predicted values from a statistical model or machine learning algorithm. In other words, it represents a difference between the actual outcome and the predicted outcome. The error term is usually denoted as epsilon and used to capture the unexplained or random variability in data. It is an important concept in statistical regression models where the goal is to estimate the relationship between a dependent variable and one or more independent variables. So very simply, your model tries to predict something, right? And usually the predicted outcome is, let's say, y dash, and your actual outcome is y. So if you want to see how far apart y dash is from y, the difference between the two, or the distance between the two, is your error term, right? That's as simple as it gets. There's one of these is the actual values, one of these is the predicted values. Now, as a machine learning researcher or a developer, you want to know how well your model is doing, right? So you want a measure of this deviation. So that is typically the error, how far off your model is from the actual value. Whereas the loss function, also known as a cost function or objective function, is a mathematical function that measures the discrepancy between the predicted output and the actual output for a given input in a machine learning model. The goal of machine learning is often to minimize the value of the loss function, as it quantifies how well the model is performing in terms of its predictive accuracy. Different types of machine learning algorithms may use different loss functions depending on the specific problem being solved and the type of data being used. So if you've worked with machine learning, you would have heard a few different types of these cost functions. Maybe you've heard of cross entropy loss or something else like that, right? If you want to think of simple examples of loss, you could think of maybe mean square error, right? The mean of all the errors and the square of that. That could be one thing. You could have something like RMSE, which is root mean square error. So basically it's a function on top of this error, right? That's what the loss function is. And you might choose different functions based on your kind of network and your application. And this is basically building on top of the error term to, you can think of it as a mathematical model or a function that associated with this error term. So it might take this error term and say square it, or take an absolute value of it, or something like that, right? There are different forms of objective functions, and it might be a little more complicated than the simple examples that I'm giving you also. But there are a lot of these loss functions. So you can think of it as a function on top of this error. And depending on the machine learning algorithms, you can use different loss functions. Okay, so to summarize this answer, the error represents a residual between the observed data and predicted values, whereas the loss function is a mathematical function used to measure the discrepancy between the predicted and the actual outputs in a machine learning model. Right. So we typically, in deep learning, you'll hear the loss function being used a lot in all this back propagation and gradients and things like that. In things like linear regression, people will still talk about the error term, right? But they're very related, but they might not be the same. One case where mathematically they are the same is the loss function is equal to the error term. You could have such a thing depending on the algorithm and the data that you're using, but more often than not, it will be a function on top of the error term. So that's how these two are related. Right. Yeah. So depending on all of these terms, you'll see different cost functions being used. Okay, I think that's all for that question. Okay, so here's another long question. So let's see. This is about the forward and the backward partial derivatives. Once we compute z from inputs x and w, we can compute dou z by dou x and dou z by dou w while computing the forward pass. Similarly, for other nodes, we can compute their respective derivatives. So I was wondering why we need to compute these only after the node j is computed fully. So this is the difference in terms. Yes, the error term is the difference in the actual and the predicted one, and this whole answer expects the difference in the terminology that's used, error and loss. These are again like the ML community tries to come up with some standardized terms, right? Because you don't want one person talking about error and another person talking about loss function and then both of them meaning the same. That's very confusing, especially for someone new who's trying to understand and learn the field, right? You might see different, it still happens, you might see when a field is very new especially, you'll see different research papers using different terms for the same thing. That's very confusing. So after a while, the community kind of decides, maybe formally or maybe even informally, decides on a particular terminology and what it means, right? So error term and loss function by now are pretty standard. Wherever it is used, this is typically what it means. But it's important for you to be aware of this terminology so that you don't use them interchangeably. They are not interchangeable. Okay, continuing. So this person was asking, why do you need to compute the partial derivatives after the backward pass? I mean, during the backward pass. Why can't you do it during the forward pass? So is there any dependency issue, say calculating dou A by dou Z needs to be done only after dou G by dou A is computed? Since there are 5 steps involved in this illustration for the calculation of loss function J, and another 5 steps need to be done after that for calculating their derivatives. Because the calculation of the derivative can be done in parallel with the sequential execution of the node to save time. Is this so, or did I miss something? Yeah, again, before we get into the answer, so a lot of things that you study in this course, right, about the theoretical aspects of ML, like the backward pass and the forward pass, they are kind of intended to help you understand these concepts clearly. But if you want to see how this is optimally done, you should look at some of the popular frameworks and how they implement it. So TensorFlow and the PyTorch are the popular deep learning frameworks, right? So if you go look at PyTorch is completely open source, so you can look at the code. So if you see PyTorch's backward prop, if you see, there is a part called AutoGrad in PyTorch, which actually is responsible for these gradient calculation. So if you actually go study some of those things, you don't even have to look at the code. There are various blog posts and videos that talk about how this is done. You'll see how the frameworks do this in an optimized way. So that might not be equal to what you studied in class, because this is the theory. So we are just taught what are the steps involved. But that might not be the most optimal way of doing it. And when you do it in practice on real hardware, most frameworks will try to optimize for performance, for memory, for various things, right? So one thing, for instance, is you could have an approach like this. So the main thing that you have with this, right, with computing it in the forward pass and with storing it, is the memory increases, right? So if you have that amount of memory, you could do it in the forward pass and save it, and that will actually save you some time in the backward pass. So that's perfectly fine to do. If you don't have that memory, sometimes you might not even have enough memory to store all of this. Then you might want to do all of it during the backward pass, or you might want to do some of it during the forward pass. So there are a lot of such optimizations that frameworks do. I think the term for this is gradient checkpointing. So there are a lot of advanced algorithms and implementations that have come up even recently, as recent as maybe 2-3 months old in PyTorch. I think with its 2.0 release, those features have gone in. So they actually try to optimize this. Which parts of the computational graph should I store it? So it's a trade-off, right? It's typically a trade-off between runtime and memory. So if you had as much memory as possible, you could save it, and you don't, and that way you save, your time goes down, your memory goes up. If you do the other way, you don't do it in parallel and then you do it at a later point in time, your time goes up and your memory comes down. So if you are either constrained or time on or constrained on memory, you would go with one of the approaches depending on what is your constraint. But let's say if you want to kind of find a midpoint between the two, there are schemes that do partial computations. So some of it is recomputed, some of it is stored, right? That way you get a point in operational point between these two. It's neither this extreme nor that extreme. So if you want to understand some of these things practically, you should look at a framework and how it implements it. Now let's go to the answer and see what it says. So in a neural network, during the forward pass, the input data X is passed through the layers to compute the output using the learned weights and the activation functions. The computed output Z is then used to calculate the loss or objective function. During the backward pass, the gradients of the loss with respect to the output are computed and then used to update the weights through the process of backpropagation, which involves calculating the derivatives of the output with respect to the input and the weights. The reason for computing the derivatives during the backward pass after the forward pass is complete is primarily due to the chain rule of calculus. The chain rule allows us to compute the gradient of a function with respect to its input by sequentially multiplying the gradients of intermediate functions. In a neural network with multiple layers, the output of one layer serves as the input to the subsequent layer, and the gradients are multiplied in a chain-like manner as they are propagated backward from the output layer to the input layer. If we were to compute the derivatives during the forward pass, we would need to propagate gradients from the output layer to the input layer at each step, which would require keeping track of intermediate gradients and performing complex computations. So this answer basically says that since you have this chain rule coming in and you have this propagation of gradients back to the input, it will not only increase the memory usage but also increase the complexity of your computations. So this would significantly increase the computational complexity and memory requirements of the training process. In contrast, by computing derivatives during the backward pass, we can efficiently calculate the gradients in a sequential and memory efficient manner, leveraging the chain rule to propagate gradients in the network. Additionally, during the forward pass, the intermediate values are required for computing the output, but they may not be needed for computing the derivatives. Again, this matters because of memory. So you already need intermediate values to compute the output for the forward pass, but you might not need that for the derivatives. So you're adding more to the memory requirements of the forward pass by doing this at the same time. So we can avoid unnecessary computations and memory overhead during the forward pass, making the training process more efficient. But you're correct that the derivatives of the loss function with respect to the output can be computed in parallel with the sequential execution of the node value calculations. In fact, this is how most modern deep learning libraries such as TensorFlow and PyTorch are implemented for efficiency. In the illustration, we've presented the steps sequentially for the sake of clarity and simplicity, but in practice, the computation of the derivatives is done using an algorithm called backpropagation, which performs the calculations in a more efficient and parallelized way. So here, the backpropagation kind of refers to how the frameworks implement this backpropagation. During backpropagation, the derivatives of the loss function are calculated recursively, starting from the output layer and moving backward. As each node's derivative is computed, it is immediately used to update the gradients of the parameters associated with that node. This allows the computation of the derivatives to be done in parallel with the forward pass computation, which can significantly speed up the training process. Yeah, so that summarizes the answer. Basically, mathematically, there will be nothing wrong if you do this part of this computation in the forward pass. There is no dependency as such, right? What changes is your memory usage, and you might have some additional complexity in managing these gradients and propagating them to the previous layer, right? But if you manage that, like most frameworks do, then you get a speed up in terms of the training time. That's basically it. Hope this was clear. And a lot of machine learning research actually tries to optimize the training time, right? So, and if you kind of violate uh, back propagation theoretically, then proving that the network converges becomes a challenge, right? So maybe I'll just talk about one of these. Yeah, there is a lot of scope for research in this direction, and there's already been a lot of research. So, for instance, so we have this, I don't know how many of you are familiar with it, but we have this term called mini batch, right? So, when we talk about stochastic gradient descent, so there are different variants of that, where for you can do a gradient update after you actually use up all the samples that you have in your data, or you could do a gradient update after every single sample, or you could have something intermediate between the two called a mini batch, right? So the mini batch form of SGD is commonly used. So what, and as you can imagine, the backward pass calculations are a lot more intense. So typically if you look at the time taken by the forward pass and the backward pass takes almost 2 to 3x, right? 2x is very common. Sometimes it could also take 3x of the forward pass. It takes that much more time. So what people have tried to do is to come up with some pipelining schemes. So you have already kind of looked at some basic pipelining from the architecture point of view, right? This is software pipelining. So as a developer, can you make use of this pipelining concept to get a more efficient time, right? More efficient training time. So let's say typically what you would do, this is your mini batch 1, and let's say you do forward pass and then you do backward pass, right? And then it looks something like this. And many a times there are multiple GPUs involved in this, right? So you might do something like a distributed, this is called DDP in PyTorch, it's called distributed data parallel. So you might do something like a forward, backward in all the GPUs. So now essentially what happens is your batch, let's say your batch size here is 4 and you have maybe 8 such GPUs doing, right? And at the end you will have to do a gradient update across all of them. If you do a gradient update here alone after this 4, here alone after this, and here, then the model kind of starts diverging, because even though you're training across 4 GPUs, ultimately you want one single model. So what is then done is, after this mini batch completes, there'll kind of be a synchronization between all 4. Again, this can happen in different ways. One common way that's used is called a parameter server. All of these 4 send their gradients to a common centralized server, and then the aggregation and the weight update is done there and conveyed back to the GPUs. So essentially what happens is your effective batch size becomes 4 into 8, 32. It's just that multiple GPUs are doing this 4, 4, 4, 4 instead of one single GPU doing the 32. So this is the basic distributed training setting. Now on top of this, people have spoken about different forms of pipelining, right? Saying, where they talk about things like, let's say the first mini batch is in its forward pass, and even on a single GPU something like this might be feasible. So the first one is in its forward pass, and then you have the backward pass. Instead of starting the second one here, I start the second one here itself, right? And I do the forward pass here, and then I do the backward pass here, and I again, the backward pass might be, remember I said it might take 3x, right? So it might still be going on, and then I might start my third forward pass here, and so on, right? But now, depending on where you do this weight update, you might lose, mathematically you might not be doing SGD anymore, and then convergence immediately comes into play. So whether it converges is a question, right? So a lot of research tries to prove that whatever alternative pipelining mechanism they propose actually converges. So pipe dream was one of the first papers to try out something like this. It was around, I think, 5 years ago. There's been a lot of research in this direction. So, yeah, ultimately the goal is to get efficiency without compromising correctness, right? Because the moment you go away from what is traditional backprop with STD, you no longer have a guarantee that the model will converge, right? And without that, it doesn't make sense. No matter how low the runtime becomes, your model might have very low accuracy. Let's say your top accuracy was 90%, and after your new scheme of optimization, the accuracy comes down to 70%. So no one's going to care if you brought the runtime by down to say zero point 0.5 or 0.2x, right? Even all those improvements that you get in runtime will be useless as long as you don't get a good accuracy. Federated learning is slightly different from typical distributed learning, because in federated learning privacy is a strong focus, right? So here what happens, you're okay sending data to different um, devices, right? So for instance, let's say I have all my data in a particular storage, and what I simply do is partition this and send this to different GPUs, right? That is traditional distributed learning. In federated learning, you don't actually do this, as in if certain data is generated on a device, it is kept on that same device. Calculations and updating on a central server, yes, that idea is different, but again, because of the privacy constraints, how that is done slightly differs, right, from typical distributed and federated. So in federated, the key idea is that, because if you send, let's say if you send the gradients to the central server, then there has been research work, I think, that has proved that based on those you can actually get the original data, or you can get some information about the original data. And in really privacy constrained settings, you might care about that also. So there should be no data leakage from whatever you send to a central server. So in federated learning, I think only the final outputs are sent to the central server. In distributed learning, it's a little more fine grained. You can send your gradients and then the server can do the aggregation and then get the weight. So that's more or less the difference between federated learning and distributed learning. And again, look this up. It's been a while since I've gone through this, but that's the broad idea. Federated learning has a lot more focus on privacy, and therefore you have a lot more restrictions on what you can send to a central server. Is that clear? Yeah, the weights are probably sent in federated learning. In distributed learning, you can send the gradients themselves. Right, you can look that up. You can look up the difference between distributed learning and federated learning, right? You will get to know clearly what I'm talking about and why it's important, why that distinction is important. Okay, so yeah, I think this is the last question. So this is about the CSR format. So there are only 7 values in the example, but PTR shows the last value is 8. Question is that since there's no value for PTR 8, is it an error or does it have some purpose in the calculation? So the answer is, so this is the example that was discussed in class, right? So your PTR has 0, 2, 4, 7, 8. Now the question is, there are only 7 non-zero values, 3, 4, 5, this, right? This index I think is what the person is talking about, 3, 4, 5, 6, 7, 8. Yeah, there are 8 values but just 7 indices. So the answer given is, the PTR array is an integer array of length n plus 1, where n is the number of rows in the sparse matrix. Each element of the PTR array corresponds to a row in the sparse matrix, and its value represents the index in the call and val arrays where the rows non-zero elements start. This part I think you already know. The value of the last element in the PTR array represents the index in the call and val arrays where the non-zero elements of the last row end. Since this is the total number of non-zero elements in the sparse matrix, it can be used to allocate memory for the call and val arrays in advance without having to iterate over the entire sparse matrix to count the number of non-zero elements. Right. So the basic idea with having this value is that it quickly gives you the number of non-zero elements, and that is the size of both the call and the vals, both these arrays. So you can easily allocate memory for both of them by just looking at this value, right? That's the only point of storing it. It doesn't serve any other purpose in the calculation. Great. So with this, we come to an end of the discussion forum questions. Before I move to the problem solving, are there any doubts on all the concepts that are covered in week 12? Because like I said, we are skipping the recap this week. So if you have any doubts, you feel free to ask. I'll pause here for 30 seconds. Okay, how much do you need to understand gem optimization as a programmer? It depends at what level you're programming, right? Let's say you're writing CUDA code, then you need to understand it a lot in detail, right? Because you're going to be writing these optimizations, and unless you do it, the compiler might do a few optimizations, but many of the things are supposed to be done by you. But if you're writing, let's say, model code in PyTorch or TensorFlow, then as you're rightly saying, optimizations are taken care by the framework, right? So then you don't really need to understand these in detail as a typical end user. But let's say you're actually trying to optimize some custom neural network. So you should understand the basics of optimizations, so that if you profile that workload and you get some information on this is what is happening, you should be able to understand what are the optimizations that are being used. Can you do something better, right? Because frameworks again cater to the common case. This is a common philosophy in system design. I think the one line explanation for it would be make the common case fast. So if you're trying to optimize anything, you try to first optimize the thing that's most commonly used, right? You as a student also might be doing that. You'd say, okay, this is a definite question, it's going to come in the exam. So first, let me prepare for those. A lot of people do that, right? That's why they refer to things like question banks, previous year's question papers. So the way frameworks and a lot of systems are implemented is they try to optimize the common case. So like we saw, convolution is a fundamental operation in deep learning, and convolution has a gem implementation. That's why all your frameworks and compilers will try to optimize this gem operation. But let's say as a researcher, you might be coming up with a new network that does not use this, right? It might use some custom operations. Now the frameworks don't really care about this because no one is really using them. You might be among the 1% or 0.1% that is using this operation, right? So you will not find it optimized either by the framework or at lower levels, right? Closer to the hardware. So then if you are trying to optimize this, or you're trying to even show to the community that this is a valid network, if your network has a runtime of 10x the runtime of whatever is the most popular one, then it's going to be hard to get your network accepted, right? Because the community will say, okay, maybe your network gets the same accuracy, but if it's 10 times lower, I don't really want to take the pain of understanding this and adapting to this. So you need to first prove that it can be fast enough, right? So then you end up having to dig deep into these lower levels that typically a programmer doesn't have to use, but you will need to, because you're doing something new. So the long answer is, as long as you're doing something that's common and typical, the framework takes care of you. The moment you venture into the unknown operators and the unknown layers category, then you will need to know how these are done, and you might need to even implement some of these yourself. Is that helpful? Okay, great. Yeah, that's a good understanding to have. It's a good question to ask, and you should always ask that question about whatever you learn, right? How important is this for me? Where can I use this concept that I'm learning? So it helps you put things into perspective. Okay, so let's get started with today's problem solving. So again, we have this format throughout this course. I think there are a lot of questions like this where the data is common for 5-6 questions. In a way, it might be advantageous during your exam because you read this data once and then you're able to solve 5-6 questions. But from a live session point of view, it definitely is challenging to keep switching between multiple slides. But let's see, we'll try to do the best we can. So this says, consider a neural network with the following layer configurations for a 1000 class classification problem. We train using stochastic gradient descent. Instead of passing the entire input dataset at one go, we iterate over the dataset, and for each individual input example, we perform the forward pass, calculate the loss, and then perform the backward pass to update the training parameters. The dimensions of the input image is 3 cross 224 cross 224. The layer specification is as follows. Layer 1, convolution layer with 64 3 cross 3 filters, stride 1, padding 1. Layer 2, max pooling 2 cross 2 filters at stride 2. Layer 3, convolution 128 3 cross 3 filters, stride 1, padding 1. Layer 4, max pooling layer 2 cross 2 filters at stride 2. 5, again convolution 256 3 cross 3 filters at stride 1, padding 1. 6, convolutional layer with 256 3 cross 3 filters at stride 1 with padding 1. Layer 7, max pooling layer with 2 cross 2 filters at stride 2. 8 is again convolution, 9 is convolution, 10 is max pooling. 11 is convolution, 12 is convolution, 13 is max pooling. And after this, the 3D image volume of dimensions CHW is linearized to a 1D vector comprising C cross H cross W elements and fed to the following fully connected layers. 14, fully connected layer with 4096 hidden units. 15, 4096 again, and 16,000 hidden units. So the 16 yields a list of 10,000 activations that represent the probability scores for the 1000 classes in our classification problem. So this is a long 16 layer network, so don't try to note down all the layers and all the parameters. Whatever the question asks, I will move to that part of the network and you can look at it and solve it immediately. So the first question says, What are the number of channels for the output image volume of layer 1? Options are 64, 224, 32 and 3, right? Output image volume of layer 1, number of channels. This is the question. Now I'll pause at the layer 1 for 30 seconds and come back to the options. And then you can take a couple of minutes to solve it. Okay, I hope you've had a chance to look at layer 1. Let's go back to the question and you can take 2 minutes to solve this. Thirty more seconds. Some of these questions you might not have directly done it in class, right? You might have only discussed what a network architecture looks like, what's a convolution layer, but think about it, because it's, you might also get such questions in the exam, right, where you've not done something like this in class, it was not exactly done, but you're asked to kind of come up with that. Okay, we have one answer saying 3. Anyone else? channel will be 3. Okay, let's look at it. So it's actually 64. So let's look at the layer 1. So we have 64 3 cross 3 filters, right? Now remember, your input image has 3 channels. But if you remember that picture that we had in week 11, right? What happens to these 3 channels after the convolution layer? They are summed up, right? There is an element wise addition. So this essentially goes down to 1. So your number of channels that you have after a convolution layer will basically be equivalent to the number of filters that you have. That's why it is 64 and not 3. Yeah, so this is what it says. Number of filters is 64 for layer 1. So we have 64 channels in the output image volume. So if you think of the channels as in the input image, right, it's easy to kind of think of these channels. You think of it as RGB. But once you come to this filters, it's different. It's no longer, it doesn't have that same connotation. But the number of channels will be equal to the number of filters. That's typically what we see in a convolution layer. And why that is? Because you do this element wise addition that you saw in week 11. So if you are a little confused about what happens in a convolution layer, you should go and look at that slide from week 11, which shows an image with multiple channels and multiple filters, right? And I remember this picture that was there. So the filters act on all of these channels, and then ultimately you do an element wise addition across the 3 channels to get one output time. So that's how it is. Okay, so we are almost at 8 o'clock, so maybe we can take a break now and come back at 8:05 and do the questions. So I think we have 1 hour, so that's enough time to finish the rest of the questions. So see you at 8:05. I'll keep the call running. Feel free to take a quick break. Okay, let's continue. For that, we have a question. Okay, tips for exam preparation. Okay, 20th of March. What you can try and do is to go through the slides, right? So you'll get a little bit of an idea, and some slides might be easy for you to understand because let's say you've watched the problem solving sessions, right? So after that, you can, for whatever you understand, you don't need to go back and watch the videos. For whatever you don't understand, you can go and look at that concept being explained, and that way you'll understand it a little better. And what else can you do too? And if you're comfortable watching it at a faster speed, that's also something you can do. You can watch it at 1.5x or even 2x, whatever works for you. That way you can kind of cover it in a shorter amount of time. But yeah, if you have been able to do the assignments of all the weeks and go through the problem solving questions, then the exam should be doable, because from what I heard, it was completely MCQ based, no subjective questions. So problem solving sessions will give you a good handle on how to solve those. But yeah, the theory might see, so there are always some questions in an exam which are kind of very similar to the problem solving questions that we've already done, and some questions that are new, right? Every faculty and set of TAs will try to have a good mix of the two, because the questions are intended to make you think and see if you've really understood the concepts. So by solving just the problems properly, you might not be able to answer all the questions, but since you say you're short on time, that is a good starting point. So once you cover all the problem solving sessions and the assignment material, and you've gone through the slides, that will give you a bit of confidence that okay, you've prepared for the exam reasonably well. Now if you still have time left, I would recommend trying to watch the lectures, and like I suggested, you can watch it at a faster speed so that it doesn't take that long, right? So it's, I think, 2 hours per week's content, and you might be able to finish it in 1.5 or even 1 hour, depending on what speed you watch it. But that you can do later once you have a good handle on the problems and the solving. But again, to do that, right, if you've not at all attended the week's session, going through the slides would be a good starting point. um, that is a tricky question, so I don't know, because I have not seen even one previous NPTEL exam part, so I'm not really sure. I think from the first set of sessions, the kernel launches, and I saw a lot of questions on the kernel launch and the launch parameters, right? And that sort of questions might be easier to solve, and once you solve a few, you kind of understand all of them. Theoretical questions, again, from the initial introductory parts, you will see a lot of them. And so yeah, going through those week's content, right, week maybe 1 to 2, week 1 and 2 would help you answer some of the theoretical questions also. So that should give you a reasonable thing. But when exactly is the exam? How much time do you have from now? Oh, 29th. Okay, you don't have a lot of time there. It's just a week. Okay, so I see. Yeah, so that can be a lot then. So, yeah, so then you can try and do some parts from the initial. So look through the syllabus, right? See, there is that initial slide that you have in week 0 or week 1 where they talk about the syllabus. Look through that, and you'll kind of get an understanding, even based on these live sessions, right? For instance, here you see a lot of, in the last 2 weeks, if you ask me what was important, I would say things like this: calculating the dimensions of the convolutional layer, things like that. But again, disclaimer, I'm saying all of this as somebody who's teaching the course for the first time. I am not involved with setting the exams, nor have I seen previous exam papers. So it might or might not be true. I'm just trying to help you out, given that you have a short amount of time. So keep that in mind. And I'm saying this just because people on YouTube will also be watching this, so I don't want them to get the wrong impression. But yeah, try to look at the live session slides, right? And you will see in each session there are a certain number of problems which dominate. 7 out of 10 questions might be something similar, right? So if you get the template of those questions right, for instance this kernel launch that I was talking about, or questions similar to what we are discussing, then one of those topics is kind of covered, right? So try and do that, and if you've solved a good number of problems, that itself will help you more or less. I don't think you have time to watch all the videos, so that's okay. So try and see for these questions that are repeated a lot, see if you can, if you are unable to solve any of them, see if you are able to watch the video corresponding to that, so that it will help you solve more of those questions, and it's more likely that some of those questions will also turn up, right? And theoretical questions, I think from the initial weeks, and maybe even that introduction to OpenCL, that those were the parts I think I saw a lot of theoretical questions. So yeah, this much should be helpful, and try and solve it when you get your exam paper. Try and solve the questions that you know and that you can kind of finish off before trying to sit with the things that you maybe, if you've not gotten the time to study, right? Some of those questions might look very unfamiliar, but if you have time, if you finish off all the ones that you've known, then you can spend some time thinking about these questions. You might not know all of the details, but by now I'm assuming you attended at least five, 6 live sessions, right? So you would have heard of the concept somewhere. Try and recall what little you know and see if you're able to solve at least part of the question based on that, and that way you can rule out some of the options and make a calculated guess on what it is, right? So yeah, don't worry about it too much. I know it's a week away, so it's a bit scary, but yeah, do the best you can under the constraints you have, right? That's all of us can do. So yeah, and all the best to everyone taking the exam. Hope all of you do well. And this is an advanced course, right? So the fact that you've taken this course and you've come this far shows that you're really interested in the course and you've been persevering enough to stay till the end. So don't worry about the exam too much. It'll be fine. Okay, glad to hear that. Yeah, sometimes advanced courses are like that, right? That's why you have these live sessions, so that you get a little bit of interaction and it feels less daunting. Sometimes you build up the exam a lot in your head and you think, oh, it's going to be so tough and I can't do it. But if you've been watching these live sessions regularly, it should definitely help you solve at least some of the exam questions, right? So don't worry too much. It won't be all unfamiliar and new. So that's why we have challenging questions in the live sessions, right? You might sometimes think that the assignment questions are so difficult and the live session questions are also so difficult. We didn't really cover this in the class, but by learning how to solve these questions, you are kind of preparing yourself for challenging questions. So there can't be things that are much worse than this. If you've done the assignment questions and if you've done the live sessions, you're pretty much well prepared for the exam. Don't worry too much. Just try and revise whatever you can in the little time that you have. Okay, with that, let's move to the next question. So we finished question 1. Okay, so what are the height and width of each image in the output image volume of layer 1? 227 cross 227, 221, 220, 224. So I'll again pause at layer 1 for a bit. This is layer 1. And then we'll go to the options and wait there for 2 minutes. Okay, we have one answer saying 227 cross 227. I'll pause for another 30 seconds to see if anyone else has an answer. Again, this wasn't discussed in class directly maybe, but think about it. How does a kernel slide over the entire image? And depending on that sliding, what is the final output dimensions that you get? right? That is basically the question. Okay, let's look at the answer. It's 224 cross 224. Okay, now we have an answer saying 220, but let's see why it is 224, right? So here is kind of a formula which says 1 plus, this is the input dimension, minus f plus 2p, right? And divided by s, this whole thing divided by s. And this is a standard formula that you'll find in many deep learning textbooks and blogs and things like that, which talk about convolution. So first let's just try substituting this. So here f is the filter size, which was 3, and p is your padding, which was I think 1, so 2p will become 2, and s is 1, so there's no division actually happening. So 224 minus 1, and then there is a plus 1, so you end up with 224. So now what you need to do, so ultimately the answer is 224 cross 224. But if you really want to understand this formula itself, right, I would suggest take a very small image, take a very small, it doesn't have to be an image, just think of it as maybe a 3 cross 3 matrix, and think of maybe a 2 cross 2 filter that you have, right, and play around with maybe first just the stride. Say if the stride is 1, what is the output dimension going to be, and try and do this with the formula, and then add one more dimension, add the padding, right? So in class we studied padding of 1, and when we say padding of 1, we are actually adding the this much more, right? We are adding 1 here and 1 here. So yeah, so in this case it remains the same. That's also something interesting to notice, right, that it remains the same, but in some cases it can reduce. You should also ask yourself, can it actually increase, right? Think about that, think about this formula, and think about when it would increase, right? And another thing that you'll see often is, you might be asked, for instance, when will, another way of putting forth this question is, when will the height and width remain unchanged? What values of stride and padding? You might be given 4 options. So if you notice here, you will, and if you work this out, right, you will see something like 2p minus f equal to, with a stride equal to 1, right? If the question says the stride equal to 1, when are the input and output dimensions the same? You will see a relation like this, 2p minus f equal to minus 1 or something like this, or you can rewrite this as f minus 2p equal to 1, right? So that can be a generalized thing. So it's not just that padding is 1 and stride is 1. So you can come up with relations like this. I'm just trying to see if this is all you need. There is a relation like this, look it up. I don't exactly remember it, but based on this you can figure out when the input size and the output size will remain exactly the same, right? So this question could be rephrased as something like that. So you can just work it out based on this. In case where padding increases and stride remains 1, okay, stride remains 1 and padding increases, okay, we can have the size increased. Okay, that's a good observation. Yeah, so all of these can be different ways of asking the same question, and I think one of the references mentioned in this week, right, the CS231N, the course from I think Stanford, that is also a very standard source for all of these calculations. So you might find this formula that I mentioned also here. Feel free to look it up, right? But this is the answer for this convolution layer, and this is a general formula that you can use across all convolutions. You just need to substitute the input dimension, the filter, the padding and the stride. That will give you the answer. So hope this was clear, and work it out like I said with a toy example. That will also show you exactly why this is right. And if you another way of doing it without this formula, I always like to tell this that try you should be able to do things from first principles, so that if you forget a formula you're still able to do it. So another way to think and do this is look at convolution as dot products, right? Or look at convolution as a matrix multiplication. So if you look at convolution as a dot product, you will kind of be able to see how many of those dot products are there. So you can try out some of those things based on what you've learnt in class. Again, it requires you to understand. If you have to derive this formula on the fly, it requires you to understand a lot of the details very well, right? You should understand how this stride is and how the convolution is actually implemented. But if you do, then you can actually derive this on the fly. So choose between those two approaches always, whatever works for you. Okay, so we are running out of time, so I'll start going to the next one quickly. What are the number of channels for the 3D image volume of the output of layer 2? 64, 32, 16, 8. So let's go to layer 2. Layer 2 is a max pooling layer with 2x2 filters at stride 2. Also, you know what was the output of layer 1 because we just looked at that, right? We said there would be 64 channels of dimension 224 cross 224. So now that's the input to this. Think about what the output would be. So I'll scroll back. Yeah, this one. Okay, we have one answer saying 64. Let's look at the answer. It is 64. So the output of layer 1, as we discussed, was 64 cross 224 cross 224. Remember that this is a pooling kernel. So we discussed what a pooling kernel does, right? It takes either the max across a window or it takes the average across a window. Either way, it does not affect the number of channels. Channels will remain 64. Hope that is clear. Let's move to the next question. What are the heights and widths of each image in the 3D image volume for the output of layer 2? So it's the same layer again. So it's that pooling layer of 2 cross 2. Yeah, 2 cross 2 filters at stride 2, right? Now you're asked what is the height and width of each after that output, basically after layer 2, and here are your options. Think about that. Okay, we have one answer, 112 cross 112. Anyone else? It will converge in the sense. Okay, so do you mean it will decrease? It will decrease to what? Okay, it will decrease. Let's look at exactly what it is. It is 112 cross 112. So a pooling operation with stride 2 and a 2 cross 2 window size reduces both the height and the width by a factor of 2, right? So if you take a pooling kernel of 2 cross 2, right? Now ultimately across this 2 cross 2 window you are getting one value. Now if it's a stride of 2, then there is no overlap, right? It's going to be like this. So this is an easy thing for you to imagine, right? Let's just think about this is what, a 4 cross 4 matrix with a 2 cross 2 window size and stride 2, right? Now earlier you have 16 elements. Now after this pooling window is done, you get one element here, one element here, one element here, one element here. So it's a reduction by a factor of 4. So when the stride is equal to the window size dimension, it means that it is non-overlapping. So the pooling operation by definition means that you will get one value for every window, right? So how many windows do you have is essentially the question. You will have that many values, and if you're talking about the reduction, it reduces by a factor of 4, which is basically the product of this, right? And or the other way of putting it is it reduces by 2 in one dimension and 2 in the other dimension by a factor of 2. So earlier you had 224 cross 224. So both width and height reduce by a factor of 2, which gives you 112. So whenever you are asked about big images like this, a simple way is to take a small image, try to retain the same filter size and the stride and work it out, and then apply whatever you learn from that to a bigger image. Hope this is clear. Okay, if not, ask me. I'll move ahead because we have half an hour left. What are the dimensions of 3D image volume produced by layer 4? So remember layer 2 outputs were sized 112 cross 112. Now we are asked about layer 4. So let's look at both layer 3 and layer 4 definitions. Layer 3 is convolutional layer with 128 3 cross 3, and this is layer 4. Take a bit of time to look at this and then I'll move back to the options. Okay, hope you had time to look at this. We'll now look at the question which was layer 4. Yeah, these are your options. Okay, we have one answer. anyone else? Okay, let's take a look. Yes, that is the right answer. So remember, after layer 2 we had 64 channels of 112 cross 112, and after this there was a convolution layer, and because of the number of filters there, the number of filters was 128. So now the channels changes to 128, and the height and width were not affected. Again, you can use the formula and verify this. Now after this there was a pooling layer, and that reduced the image dimension to 56 cross 56, but it did not change the number of channels. So the number of channels is 128 and the image dimensions is 56 cross 56. Again, it's all the same, because if you see the network, right, we mostly have convolution and pooling. So once you figure out how to do it for these two, everything else is pretty much the same. So I think you can understand this, but I'll anyway pause here for 30 seconds. Does anyone have a doubt with this? Okay, I'll take that to mean there are no doubts. After the linearization process post layer 13, what is the total size of the 1D vector passed on to the subsequent fully connected layer in layer 14? So this is asking you about the output of layer 14 or 13, sorry. Yeah, output of layer 13, and we were still at layer 4, so you'll have to do quite a bit of computation, but try to use whatever you've learned till here, because it's more or less the same with the other layers. So I'll pause here for 30 seconds, and then at the next slide also for 30 seconds. Okay, I'll pause here for another 30 seconds, and then we can look at the question. Okay, let's move back to the options. This must be a lot of computation for you, so maybe I'll give you 2 more minutes. After layer 11, channels do not change. What's layer 11? Convolutional layer. Yeah, it is 512 filters here and 512 filters here. Channel 10 in the sense, I don't see 10 channels anywhere. Oh, after layer 10, is it? Ah, okay. Yeah, all of them seem to have 512, so yeah, it doesn't change. All of them have 512. Yeah, that's something that if you notice, you can quickly skip past some of the computation. Any answers? Layer 13. Okay, sure. Yeah. Okay, hope that helps. Let's go back to the options. Maybe we can discuss it. Yeah, sure. So the answer is A, 25088. So let's see. So we did till layer 4, right? So 128 cross 56 cross 56. So always when you get such questions that involve lengthy computation, first ask yourself, do I need to sit and do this for all of them, right? If you have to do 9 layers computations, it will at least take you 5-6 minutes, right? So it's important to look at that. So what did we learn from the first convolution and max pooling set of layers? We learned that the number of channels will be equal to the number of channels that you see with the filters, and the dimensions may or may not change, right? Whereas with the max pooling layer, you saw that it would change and the number of channels would remain constant. So you need to use that information here. So here, and another thing, what I was actually telling you, right? So I just looked up that page and I will paste it in chat, and that will be useful. And so there is also a formula for padding and stride. So under these conditions, basically when the stride is 1 and the padding is f minus 1 by 2, the output and the input volume will remain the same. Now if you observe all of these layers, right, f is 3, s is 1. So basically the when s is 1 is satisfied, f is 3 and p is 1. So f minus 1 by 2 is 3 minus 1 by 2, which is 2 by 2, which is 1, and that is equal to your padding. So you should note that none of these convolution layers change the image's dimensions. So once you note these through things, then it takes hardly a minute to solve this question, right? So now you're left with 256 channels here. Dimensions don't change, dimensions don't change. Then you have a max pooling layer which will bring down the dimensions by a factor of 2. So let's go and then work it out from there, right? So this is question 6. So we had 128, 56, 56, and then the channels kept changing. So the channels would be 512. And so another thing that the answer does here, interestingly, is to interchange the operations, is to kind of cumulatively calculate. You can also do that, right? So here they talk about the convolution layers first. The convolution layers do not change the image dimensions at all, right? They only change the number of channels. So finally your number of channels would be 512, and the pooling layers do not touch the number of channels. So you can do directly the pooling operation separately. So there were 3 pooling layers. So this 56 cross 56 would go down to 28 cross 28 in the first pooling layer, 14 cross 14 in the second, and then finally 7 cross 7. So you are left with 512 channels of 7 cross 7. So then when you linearize, the total size of the vector after the linearization would be 512 cross 7 cross 7. That would be 25088, which you can verify. Yeah. So that's the answer. And notice that you can kind of reorder the layers like this also, because the convolution here touches only the number of channels and the pooling touches only the number of, it might not, I'm just saying, it might not always be possible to reorder the computations like this. You have to be careful about when that is doable. But yeah, this is a kind of an easy way to solve this within a couple of minutes. Okay, I will move to the last question for this data. What are the dimensions of the weight matrix pertaining to the fully connected layer in layer 15? I think this is the easiest of the lot. So yeah, layer 15, right? This is the one. So the fully connected layer is 4096. So what is the size of the weight matrix is what's asked. Any answers? Let's look at this one. I think we haven't discussed a fully connected layer yet, so you might not. So it's 4096, right? So this had 4096 hidden units, and the input vector would be of this dimension, and this also has 4096. So basically it's let's take this to be 4 right now, right? So let's take it to be 4 on either sides. So it would be something like this: 4 here, 4 here. And because it's a fully connected layer, there would be connections from every neuron to every other neuron, right? That means you have 4 connections for each of them, and you have 4 such, right? So it's 4 into 4, and no matter what this number is, it would be basically n cross n. That is a fully connected layer. So this is 4096 cross 4096. This is an easy one. Okay, so with that we'll move to a different topic. So CSR format, I think you're already aware of. So quick recap: we have 3 arrays, the val, call and the PTR. It's a 1D for way of storing a sparse m cross n. So val and call are of the same length, and this length is called n and z, represents the number of non-zero values in the matrix. Call stores the column index and val stores the non-zero value. I'll skip this. In case you're unable to solve the question, we'll come back and look at this and the example. So consider the following sparse matrix. Here you have a matrix. Assume that this is stored in a CSR format. What is the length of the vals array which stores the non-zero values? You can take 1 minute or maybe even 30 seconds for this. Any answers? We have two answers, 6 and 7, both of which are in the options. Think about which one it is. It is 6. So there are totally 6 non-zero values, 3, 4, 5 and 6. So the vals array has exactly 6 elements, right? Remember we just studied this. Val is of length n and z, which represents a number of non-zero elements. Same for call, right? So the val array actually stores these non-zero values. So it's the same as the number of non-zero values, which is 6. So this should be clear. Moving on. For the same sparse matrix, what is the length of the call array which stores the column indices instead of the non-zero values? Any answers? If not, let's take a look. This is also straightforward. Okay, this is not highlighted. Sorry about that. So the calls and the vals have the same number of the call and the vals have the same number of elements. So this would be 6 as well. So why would it be 6? Let's go back to the definition of these things, right? So call stores the column index of the non-zero elements. So if you have, let's say, 5 non-zero elements, you have to store the column index of each of them. Like you see in the example here, you have what, 3, 4, 5, 6, 7, 8 non-zero elements, right? You have to store the column index of all of them. So you can't have any less than the number of elements. So that's why both of these are equal and both of these are of the length n and z. So when you have such questions, you have to go back to your definitions. You have to think about what this represents and therefore what will its size be. So it is also 6. And now the 10th question. For the same sparse matrix in question 8, what is the value of PTR of 2? Any answers? Okay, if not, let's look at it. It is 3. So again, go back to what is the definition of PTR, right? So PTR says it stores the cumulative number of non-zero elements. PTR of I represents the total number of non-zero elements observed until the ith row. So PTR of 0 by definition is 0. PTR of I would be PTR of I minus 1 plus non-zero elements observed in this particular row. So this is very simple to calculate, right? Given this matrix, how many non-zero elements do you have in the zeroth row? 0. How many do you have here? You have 3 of them, right? So, and how many do you have here? 1. So which one was asked? PTR of 2. So for the second row, you have a total of 3 non-zero elements present, right? Because in the first row you have 3 here itself, right? So the previous one is 0 and this is 3. So the sum of both of those will be 3, and that's what you have. Yeah. So if you are confused, right, look at this example. So for the 0, by definition it is 0. For 1, there are 2 elements here, plus 0, it's 2. And for the next one, there are 2 elements here, plus 2 of these, so 4. So in a way, it's kind of offset by 1 from the actual matrix. You might get confused thinking this is row 0. Row 0 has 2 elements, therefore this should be 2. But remember that it's kind of reflecting for the previous row. So it would always start from 0 and it would be 1 offset. So similarly here, the first one would always be 0, and the second one also in this case is 0, and then it would be 3. So that's why PTR of 2 is 3. Okay, hope this is clear. Okay, so questions 11 to 15 are kind of very similar to whatever we just did. So before I go to that, do you have any other questions? We have last 5 minutes left in the session. So if you have any other questions, now is the time to ask. If you've made a note of some doubts or something, look through them and see if you want to ask something. I'll keep going on with the questions, but feel free to post your questions. Even if we don't get time to address them, like I said, I'll try and put a couple of slides on them in the next 2-3 days. So this is a very similar question. Maybe we'll solve 1 or 2 parts of it, and the rest of it with the answer is put into the slides. So even if we don't solve it in class, you can go look at it and you'll be able to solve. So it gives you some additional questions to solve. So again, it's a 1000 class classification. We train using STD. Basically, instead of passing the entire input data set at one go, we iterate over the data set, and for each individual input example, we perform the forward pass, calculate the loss, and then perform the backward pass to update the training parameters. Dimensions of the input image are 3 cross 227 cross 227. Layer specifications are here, but we'll come back to this in the questions. The only difference here is you have 6 options giving you various dimensions, and you will be asked to pick from this, right? So let's see the first questions. What are the dimensions for the output of conv1? And you have these options are anyway here, so I'll just pause here. First question is very simple. You're asked for the output of conv1. You can take a minute and solve this. If you don't have answers, let's quickly look at it. So the answer is 2, right? So the input image is 3 cross 2 cross 227 cross 227. We have 96 number of filters. So first of all, you already know that the number of channels is going to be 96. Now you need to find only the height and the width. How would you do that? You have this formula 1 plus the input dimension minus f plus 2p by s. So here s is 4, p is 0, f is 11. So just substitute it, 227 minus 11 divided by 4 and plus 1. That will give you 55 and the width will be the same. So your output dimensions is 96 cross 55 cross 55, which maps to your option 2. And that is the answer for this. Again, I think it's very similar to what we did. So even if you are not able to answer it now, after the live session you can take some time and try and solve them on your own. This will kind of reinforce the concepts and the formulae. Yeah, tell me. Since there is 4, yeah, if your options are very different, right, you can quickly do that also and see. If you have options that are very close, maybe 55, 56, 57, then you will need to put the value of f also to check. But if not, that could give you a rough guess. Yeah, that would be a good approach too. Okay, we'll do one more question and then finish up. Dimensions for the output of layer conv2. So again, let's go back here. This is your conv2. So there's a max pool layer after what we discussed. So think about that and think about what the output will be. Any answers? Three, okay. Yes, 3 is correct. So you can look through this. So you have you already figured out the conv dimensions. So now you have to put in the max pool stride and stride and figure out what would be the output of it. So you get this, and then you have 256 filters. So you're going to have 256 channels, and you have a filter size, a stride and a padding, right? So use the same formula. You already have this. You figure out the width and the height. So you end up with 27 into 27 into 256, which is your option 3. Yeah, so that's it. We are already a minute past 9. So I'll leave these questions here. They are very similar, right? They are nothing that we've already not seen. So I've made sure to cover all types of questions here. So you can solve these 3 questions on your own when you find time and check if you're getting the right answers. So the slides will be uploaded and the video will also be there. So you can use it as a reference and solve it on your own. So like I said, this will be the last live session, but continue to ask questions on the discussion forum. And if you need something from me as well, some general exam guidance or something, feel free to write to me. I think my email ID is somewhere at the beginning, or if it's not, I will leave it in the chat box or as well. So in case you want to email me, you can use this. But please use the official discussion forum for any questions on the grading and things like that, because like I said, those are the TAs who will actually do those things, so they'll be better aware of that. If you have any other general questions on the course or something like that, feel free to ask me. So with that, thank you for attending all of these live sessions. Hope you found it useful. And if you have any feedback for me that you'd like to tell me or that'll help me improve, feel free to post it on the chat box. I'll hang around for a minute more in case you have any last minute questions. But if not, you can drop off. And thank you so much for joining again. You're welcome. I'm very happy to hear it helped. That's all right. You can at least the videos and the recordings are there, so hopefully you will benefit from watching them and going through the slides. That's all right. Yeah. Thank you so much too. Thank you all. Thanks to all of you for attending and keeping the session interactive and asking questions. Right. That helps me a lot too. In a way, it motivates me. So week 9 slides, is it? I will check that right away. I thought I had posted all of them, so I'll check in case there is an issue. And today I'll make sure that all of the week slides and recordings are there. The videos you guys are able to access, right? Great. Okay. I will check week 9 right away. Thanks again for telling me. I didn't notice that. Sure. Thank you and all the best for your exam again. Hope all of you do well. Okay. Thank you.